SwayamPrabha. Digital India. Educated India.
What we have covered up till now is understanding of the first law of thermodynamics and as well as second law of thermodynamics. We are going to now start a new topic. Is going to be on the power cycles, and in particular we will start a gas power cycle. So we will try to evaluate the performance of gas power cycle in this particular lecture. Okay, before we start, let us look at the definition in general, different forms of thermodynamic cycle. So thermodynamic cycle, let's say TC, you can make use of it for power cycles. Okay, and we are going to say power cycle for those where the cycles are used by net power output devices. So cycles are used by net power output devices. Okay, so that will be your power cycle. The thermodynamic cycle can be used for refrigeration cycle, okay, where the cycles are used or cycle is used by devices to produce a refrigeration effect. Okay, so these examples would be your AC, refrigerator, okay, or heat pump. Or here the example would be your automobile engine. Okay. Thermodynamic cycle, you need to have some certain working fluid. So based on the working fluid, we can have two different forms of cycle. So one would be your, let's say, gas cycle. So here the working fluid remains gas, remains in the gaseous state, okay, all the time. And then you have this vapor cycle. So the gas, one way of making use of thermodynamic cycle is called gas cycle, where the working fluid remains in the gaseous state, and the other would be a vapor cycle, where the working fluid involves some kind of vapor liquid phase transition, and one part of the cycle would be the working fluid will be in the vapor phase, and the other cycle would be in the liquid phase. Okay, so thermodynamic cycle can be also categorized in two forms. One would be your closed cycle, the other could be your open cycle. So the definition would be, for the closed cycle, your working fluid returns back to its initial state, okay, and for the open cycle, the working fluid will not return to its initial state, but rather it will be replenished. That means the existing working fluid will be taken out from the system and the new one will be entered. So let me just describe it more. So for the case of closed cycle, you have working fluid returns to the initial state at the end of the cycle. That is, it's recirculated. For the case of open cycle, working fluid is renewed at the end of each cycle. Okay. So, the example of open thermodynamic cycle would be your automobile engine. Okay. So, in this particular open thermodynamic cycle, the gas do not undergo a thermodynamic complete cycle. Ideally, we should say this is the fluid or the working fluid undergoes mechanical cycle. Okay. So, we will get an idea of this subtle difference in the later part of the lecture. Now, if we discuss this heat engine, then we can, which basically make use of thermodynamic cycle, we can categorize the heat engine based on internal combustion or external combustion. Okay. Where internal combustion would be your, for the case where your burning of fluid occurs within the system boundary. So, this will be your automobile engine, okay, where the external combustion will be the case where the heat is supplied to the working fluid, okay, externally or from the external source. So, the source would be something like furnace, your nuclear reactor, geothermal well. So, these are the different sources. So, the example of external combustion heat engine would be your steam power plant. And for the case of IC would be your automobile engine. Okay. So, what we are going to do is we first look at power cycle first and followed by refrigeration cycle. Okay. And let me just briefly give an overview of basic consideration which we need to undertake for the analysis of the power cycle, where the idealization would be done to simplify our analysis in order to solve the problem. Okay. So, let us take an overview. So, most power producing devices will be operated on the cycle, and as I said, in order to make this analysis easy, we need to consider idealization. For example, one can consider, let us say, a potato in an oven, and it represents as a water body as an idealized model. And of course, the results need to be taken very carefully, that it should not be extended to many different systems, because there are limitations as far as the modeling is concerned or idealization is concerned. For the case of a cycle, which may be looking at this as an actual cycle in a dotted form, we can idealize this in terms of your the one, considering that each of them are this internally reversible processes. So, the actual process may not be internally reversible process, but they can be considered or represented by an ideal cycle which consists of internally reversible process. So, this is an example of taking converting an actual cycle to ideal cycle for the sake of analysis. Okay. So, an ideal cycle would be a cycle that resembles an actual cycle closely, but is made of totally internally reversible process. Now, as we know from our earlier analysis for the case of engine, that the efficiency of a engine is defined as W net divided by Q in, and we know that for the case of a Carnot cycle, which the efficiency is the highest. So, now we know that Carnot cycle are externally and internally both reversible. So, ideal cycles are considered to be internally reversible, but they may not be necessarily externally reversible, which essentially means that ideal cycle may involve certain heat transfer through a finite temperature difference. So, what are the common idealization and simplification in the analysis of the power cycles? That the cycle does not involve any friction, okay, which essentially means there is no pressure drop through any pipe or devices. All expansion and compression processes are taken in a quasi equilibrium manner, which essentially means that all the processes are internally reversible process. We will be considering all devices insulated, or in other words, we will be considering that the pipe connecting the different component of the systems are well insulated or heat transfer through them are negligible. So this will make our analysis very simple. Now in the analysis of power cycles, the property diagram would become extremely useful diagram and for the analysis. And as we have discussed earlier, the PV and TS diagram, the area enclosed by the process such as described here, it represents the W net, okay, and this is also equivalent to the net heat transfer for the cycle, for the idealized cycle, okay. Or for the case of an NS diagram, we are aware of the fact that heat addition would mean increase in the direction of the increasing entropy, okay, or in other words, heat addition proceeds in the direction of increasing entropy. So essentially, if you consider something like this, then it's very clear that this 1 and 2 3 process involves heat addition, and heat reduction will be proceeding in the direction of decreasing entropy, and asymptotic would be your constant entropy. So this is something which would be representative of changes in the entropy corresponding to different heat addition or rejection or adiabatic processes, okay. So this is something which is completely clear if you had used this Carnot cycle, which we have already discussed earlier, that it consists of 4 reversible processes. It has quite a value in our engineering application, okay, something which we can clearly understand once we describe the different engines. So the Carnot cycle composed of your heat in at constant temperature, that is isothermal heat addition, and then your asymptotic expansion, okay, which is nothing but adiabatic reversible expansion, and then you have a constant temperature heat rejection, that is isothermal heat rejection, followed by asymptotic compression, okay. And for the case of a Carnot cycle, we have already developed this relation that this can be written as simply the efficiency can be written as 1 minus the ratio of TL and TH, okay. Though the Carnot cycle provides kind of a very simplified form of a cycle where one can produce network, okay, it's difficult to implement such a Carnot cycle practically, okay, because of the fact that reversible isothermal heat transfer is very difficult to achieve in reality. So the Carnot cycle does act as a standard against which we try to develop gas power cycles, and thus we can compare the actual or ideal cycle against the Carnot cycle. One of the important thing with the Carnot cycle is that which provides an important message is that you can improve the thermal efficiency of the cycle by increasing the average temperature at which heat is supplied, or by decreasing the average temperature at which heat is rejected, okay. So that means if you reduce your TL or increase your TH, the eta is going to increase. This is a message which you can take it from the Carnot cycle based efficiency. Okay, so now in order to analyze the power cycle, where we are going to make use of gas to start with, we are going to make certain assumptions which we call air standard assumptions. Before we start listing down those assumptions, so let us try to overview this particular combustion chamber, which intakes air and fuel and undergoes a combustion leading to combustion products. Now it should be clear as we are aware of the fact that air contains predominantly nitrogen, and hence what we can do is we can consider that the even combustion products are mainly composed of air, and whatever the combustion energy is being generated can be idealized as a constant heat which is provided to the chamber or heating section. So this is a kind of a idealized form where in terms of representation. So as I said that air plus fuel combustion goes to combustion product, and there is a heating. This can be idealized in the form of that you have simply air, and whatever the energy being generated can be represented as the energy being provided to the heating section, okay, and that leading to air, okay. So considering, as I said, the air is predominantly nitrogen that undergoes hardly any chemical reaction in a combustion chamber, the working fluid which we are going to consider closely resembles air at all time, okay. So this leads to the set of assumption which we call its air standard assumption, and we are going to list down here that what we are going to consider for this case of a gas based power cycle is that the gas, that is your air, which if you are making use of air standard assumption, then air is going to be considered as an ideal gas, okay. So, the working fluid for the air standard assumption is air, which will be considered as an ideal gas. All the processes which are involved in this particular cycle, or all the processes that involves and makes up the cycle are internally reversible. The combustion process is replaced by a heat addition process from an external source, as I was mentioning in an earlier slide, and the exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. Okay. So, we will understand this combustion process and exhaust process for this particular cycle more clearly in the next lecture. Okay, so the other assumption which we are going to make use is cold standard assumption, where we will consider the air having a constant specific heat at room temperature for the analysis. Okay, so that means the Cp or Cv are going to be constant, which we are going to fix it at 25 degrees Celsius. So, we are not going to consider the variation in the temperature in the analysis of a specific heat. And the cycle which we are going to apply this air standard assumption would be called air standard cycle. Okay, and that is something which will take up in our next lecture for further making use of this assumption. Okay. So, we will end this particular lecture. In the next lecture, we will first review the operation of reciprocating engines. Okay, and so hopefully this particular air standard assumption and its utility will become clear in the next lecture. So, see you in the next lecture.